It's important to keep in mind that permutations apply to cases where the order of our selections matters and where selection is happening without replacement. In example 1, we have 7 runners who are competing in a 100-meter dash. In this case, selection is happening without replacement. Once a person finishes the race, they're not going to also end up in a second position. And we know that the order matters because we're going to track who gets first place, second place, etc. How many different complete orders of finish are possible? We know that we have 7 different runners, so there are 7 different possibilities for who will end up in first place. Once that person finishes, then there are only 6 remaining possibilities for who gets second place, 5 different possibilities for who gets third place, and so on, all the way until everyone but one person has finished, and that one person is our only option for who will come in last. Multiplying all those together gives us 5,040 different possibilities for how these 7 people could finish this race. Another way of representing that same value is to use factorial notation, which is an exclamation mark. So this factorial symbol means we take that number, in this case 7, multiply it by one number less, multiply it by one number less, and so on until we get all the way down to 1. In part B, we want to consider a similar situation, but now we're only interested in how many different podium placements there are possible. So podium placements mean first, second, and third. So out of that group of 7 runners, how many ways can we get our first place, second place, and third place runner? There are 7 possible results again for first place. One of those is gone now for second place, so we're down to 6 options, and then 5 for third place. Multiplying that together would give us our answer for this problem, but instead what we're going to do is complicate this expression a little bit to start driving our way towards a formula for permutations. What we're going to do first is make this answer look a little bit more like our answer in part A. So what we didn't have there was times 4, times 3, times 2, and times 1. But if I introduce those factors, I need to divide by the exact same values to make sure I'm not changing the value of this statement at all. Now each of those values will cancel out, so I've introduced extra numbers, extra information into this problem, but I haven't changed the answer at all. We could rewrite this then as 7 factorial all over 4 factorial, and complicate things even just a little bit more by rewriting the denominator in terms of that value that we have in the numerator. So we could take 4 and rewrite it as 7 minus 3 factorial. All of this is exactly the same answer as what we started off with. But again, we're overcomplicating things so that we can drive towards this formula for permutations. When we consider permutations, what we're going to do is from a group of size n, in this previous example, our value for n was 7, we're going to select R items. In our previous example, part B, that value for R was 3. If we compare these values, 7 and 3, to what we have expressed up there, we can generalize this into a formula. Permutations will be expressed as using this notation lowercase n, capital P, lowercase r, will be equal to n factorial, where we had 7 in our previous example, divided by n minus r factorial, or in that previous example, 7 minus 3. We'll be using Desmos to calculate these results, and we'll look at how to do that in a few examples here. But I wanted to look at how we can generate this formula to have an idea of where these results are coming from. In Desmos, we'll literally type lowercase n, capital P, lowercase r, and then using function notation, feed it a value for n, the size of our group, and a value for r, the number of items we're selecting from that group, and it will calculate the number of possible outcomes for us. In example 2, we have a nonprofit organization that has 4 officers, a president, vice president, secretary, and treasurer. If there are 20 members in the organization, how many ways are there to fill the officer positions? In this case, selection is occurring without replacement. No person can fill 2 of those roles. And we know that the order matters because we're placing people into specific roles. It matters whether you're the president or the secretary. Meaning this is a case for permutations. And in Desmos, we'll enter that notation for permutations with a value of n equal to 20, so the size of our group. And out of that group, we'll select r equals 4 members. Flipping over to Desmos, we again just have that typed in, NPR with a capital P. And we'll enter in 20, 4 for those 2 values to find that there are 116,280 different possibilities. In part B, we have a similar situation, but 5 members have indicated they don't want to serve as an officer. So what happens in this scenario is that our value for n has updated. Where we originally had 20 people in our group, if we take out those 5, we're down to now a group of 15 that we're selecting from. So instead of 20 and 4, we'll plug in 15 and 4. To get 32,760 different possibilities. Before we move on to talking about combinations, I want to look at a particular outcome from calculating permutations. This can happen with a lot of different pairs of numbers, but if we plugged in 18 and 10, meaning out of a group of 18, we're going to place them into 10 specific positions. We end up with this 1.5, etc., times 10 to the 11th. To briefly review this, this is scientific notation. So if we get a result that looks like that, let's just write it out here, 1.5878900304 times 10 to the 11th power. What that means is to rewrite this number in standard form, the way we would typically write numbers, we find our decimal place and we move it 11 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we reach the end of our number, we drop in some placeholder zeros to move 10 and 11 places. Then we just rewrite that number without the times 10 to whatever power. And in this case, that result would be 158,789,030,400. So it is possible to come up with very large results, especially when we look at calculating permutations. We just need to keep in mind how we convert things from scientific notation to standard form.